assumption is not essential, but I just want to be able to consider the most general case where they are there. And in string theory, string theory landscape is a terminal landscape. Okay. And just to go through some example, let me explicitly state that I imagine the universe starts out in A. That is a completely random assumption, and I have nothing to say about theories of initial conditions. That's a separate theoretical problem. Okay. My goal is, given certain initial conditions, what probabilities do I get for vacuum from eternal inflation? What is the dynamical effect of eternal inflation on probability? Okay. So, the input parameters for which I should be able to compute these things is essentially a matrix kappa ij, which tells me the probability per unit time for roll line that's in vacuum, let's say A, to enter vacuum B. Okay. And of course, for all vacuum here. So, the way that I've drawn it, I'm allowed to go from A only to B. So there's some non-zero entry here. B can go back up to A or down to Z, and Z is terminal, so it's not going anywhere. Okay. And these entries here are generically exponentially small numbers. If these things are really metastable on a long time scale. And that is, of course, the reason why we might suspect that anything computed from this matrix could have an enormous impact on probabilities, because it's going to involve putting together exponentially small numbers, which of course vary from each other by exponential amounts. You might have one by 10 of e to the 1 million and another of e to the 100,000, and those are very different. Well, so how do we construct a probability measure? There's essentially only one pitfall, I think, and otherwise it's fairly straightforward. What we know, at least in the terminal landscape that I considered for the example, is that our roll line is going to end up in Z sooner or later, and that's where it ends. Okay, so with some probability goes to 1 at late times, you're going to end up in Z for the same reason that with the probability that goes to 1, a radioactive atom is eventually going to decay. Okay, and so the first guess, which is not a very good guess, of how to define probabilities for the roll line, is to say, well, let me define the probability for vacuum I to be proportional to the expected amount of time that the roll line is going to spend in vacuum I on its way down into Z. And the reason why that's not a very good guess, and this is a really important point, I think, is that the lifetimes in a landscape with long-lived metastable vacuum are typically exponentially long. And in fact, they're exponentially longer than the thermalization time scale for vacuum. Even our own vacuum might live for some exponentially longer time than 10 billion years. Okay. That time is completely dead time. It doesn't buy our vacuum anything in terms of being more frequently observed. Okay. It doesn't mean that it's just going to be empty to sitter space. There's nothing there. No? Yeah. So there's a subtlety that Tom and I have been agonizing about, which is that you don't want your vacuum to be too stable either, because at some point sometimes you get into the Boltzmann-Strain paradox, that it becomes more likely to create a service by bizarre random fluctuations than in the honest old-fashioned way. And but I'd like if possible. I mean, this is a very interesting discussion, but it's going to go completely off. So I'd like to stay on track and maybe have that discussion at the end of the talk. Okay. I mean, I think it's a very interesting question, but it's sort of orthogonal. And in my view, it's a constraint. It's a consistency condition on the string theory landscape. You want that to be stable enough, but not too stable. Okay. So the main moral that I want to get out of here is that we don't want to make the mistake of rewarding a vacuum for sitting around doing nothing for some exponentially long amount of time. Okay. And these factors are huge. So as a zeroth order approximation, I want to do better than that. And what we're seeing, of course, in our own vacuum is that even if it lives for an insanely longer time, as it's subtlety, everything interesting happens at the beginning. Okay. Everything interesting happens when the bubbles were created between that time and the time when everything's thermalized and the sitter space is emptying out. It's the out of equilibrium period that's the most interesting period. Okay. That's when complex structures can form. That's when presumably observers arise. And I'll get back to that point when it comes to the question of weighting vacuum in more detail. As a zeroth order approximation, what I want to take away from this is that the most important thing is to just get into your vacuum. It's just producing it. You know, of course, you don't want it to decay very, very fast. But compared to these exponentially long timescales we're usually talking about, a good first approximation is just being interested in the expected number of times the roll line is going to enter a given vacuum. That's when there's a potential for something interesting happening. Okay. So that's what I'm going to compute. And in order to compute that, it turns out that you don't need all of the information that's contained in this matrix kappa, because you don't really care how long these vacuum live. When you're in A, you're only interested in where am I going to go next, not when am I going to do this. So what's the relative probability to decay into B or C or D? Okay. And the relative probability I can compute by dividing out by the probabilities to decay at all, okay, which is the probability from A to all the different J's you can go to. And so I get a matrix that is it contains less information in the sense that you guarantee that all of the columns here sum to 1 except for the terminal vacuum, which is still 0, and which you don't denormalize at this way, of course. Okay, so here's a vacuum A that has to go to B. Remember the drawing. B can go back up to A or down to Z, and there's one free parameter here. It has to add to 1. It has to decay at some point. And Z doesn't go anywhere. Okay, so this is important because it means that these exponentially small numbers have, well, it's not gone away completely, that epsilon might still be very small. At least we've gotten rid of some of them. And in fact, if this epsilon is very small, then we can practically replace it with zeros. And we'll have only ones and zeros in this matrix. So this is important because from this matrix you don't generically expect to get exponentially large numbers anymore. So how do you compute the probability, the expected number of times that you enter vacuum, let's say A? Well, one way to do it is to draw a tree, where you start in vacuum A, let's say, and then well, the only thing that can happen is probably 1 if you go to B. There you have a choice. You just take these entries from this eta matrix, go to Z or to A with the probability. So you draw this infinite tree, and now you look at all the different ways you could have gone into A. Okay, so there's one path with probability epsilon, you multiply these. There's another path with probability epsilon squared, and so on. And so your total expected number to get into A is epsilon over 1 minus epsilon. Then you do similar things to B and Z, and in order to get normalized probabilities, well, you divide by the sum. And you get these answers. And it's just to illustrate, it's very straightforward. In fact, it's more straightforward than this because you can show that you would have gotten the same answer that gets stopped at any time that you got back to the initial vacuum. Yeah. I'm assuming that Z is terminal in the sense that it doesn't go anywhere else. For this purpose, I don't really care why it's terminal.